So to begin with, we open up the NSS and you'll notice that there is a Project Explorer window. So we're in Sales Training Pack. And the first thing we'll go to is EBSD mode. Be aware there is EBSD setup, which is a workflow that's designed to really optimize the parameters and make things very straightforward for the user. Point and shoot mode, which is for really high resolution images at a single point. Really nice because you can tie it through with the EDS, so you can build up a full database and very good for analyzing unknown samples. And the third one is EBSD mapping. And this is typically where users will spend most of the time now. And in here we have our sample, and the one we're going to look at is a duplex steel. For those not aware of this, the duplex is a steel containing both austenite and ferrite phases. Ferrite being the BCC, so it's body center cubic, you may see, and austenite being the FCC, which is the base center cubic. Okay, so when we go in, you'll see that you have a quadrant view. Top left is electron image. Here is from the force scatter detector. It's really nice for EBSD because it's a tilted sample and this gives maximum topographical contrast. The upper right is the quadrant view output, and by whichever you want to click from the lower left quadrant under EBSD view will populate through into the upper right quadrant. So just to see a few, let's just try, say, pattern, orientation, pattern quality, index quality, and we'll do the Euler map for FCC and the Euler map for BCC, and press apply. It very quickly populates through. You can choose the red image cursor and you click on a point, and you'll see that the simulated crystal gives an idea of the orientation at that point, and you can get the lattice vector and the Euler angle all at any given point there, and this ties through to the pattern quality and to the index quality. A quick way of seeing how well these tie together is on the crystal selection quality, which is this one. Again, press apply. And the nice thing that this will give is by right clicking you get a matrix. So you want the index quality, that is how well the pattern is indexed as a function of the pattern quality, which is how good the future pattern is on the actual screen. So magenta regions are areas of concern and something you want to look at in further detail. So by double clicking on the title, you can see that generally it's indexed very well relative to the pattern quality, with just a few areas which is always going to be there. Okay, so BCC, you'll see that you pull together similar type areas. So of this grain, you'll see that generally very little variation within there. And looking at the crystal, we can see that these are all of a 110 type, whereas down here it is of a 100 type, for example. It's a way of just displaying textures within the sample. Likewise, look at the FCC. There's clear evidence of twinning, which would be to expected for the austenite. Different way of displaying the information would be in terms of pole figures, or inverse pole figures. So we'll just try perhaps a normal, and we'll do an orientation distribution function, ODF. So again, we'll double click, and you'll notice that you can look a very nice way of showing the Euler angle phi1, phi2. Look at segments through. Or on the pole figure itself, again, you can look at textures. So use the tool here, and by clicking on an area, it might make it a bit clearer. Wherever we click, you'll notice that you can highlight given areas. Other things to be aware of are strain, so that's misorientation within a grain, and Schmidt, mapping, which is a way of looking at the relative slip planes within the system. For example, the three underlying systems for the BCC, you can choose your slip system of choice. It's a bit too much detail to go into now. So yeah, full output. Final thing you want to be looking at is grain sizing and grain boundary angle. So if you press apply, you'll notice now the sizes of the grains are populated, and you can output this as you wish. Okay, so very quick run through. One place we can really add value is on the EDS. So we click on the extract map image. We're going to pull out all the spectral information, and we're going to tie that through to the EBSD data. So if we go into microanalysis and click on spectral imaging, you may actually have this may not be in Compass when you first do it. So you'll see that these are the elemental maps, which gives you some information, but there are limitations of doing it this way. So the overlay between the moly, nickel and chromium, that is the difference between these two phases, how well these are absorbed. Whereas the iron, which makes most of the material, doesn't actually vary that much across. So if you're just going for this approach, you may miss something, and it'll be hard to actually work out how to quantify the phases. So if we press Compass, which is the button here, we press Auto, and this will populate through to the phase 1 and phase 2. And by clicking on Quant Results, on the seesaw button, you can click on phase 1 and phase 2, and you see that actually the elemental composition between the phases is very similar, just slight differences in a few elements. But the Compass tool has completely separated these apart without me doing anything to say which it belongs to phase A, phase B, etc. There's a way we can really sort of add value with our EDS to our EBSD. So again, to see that in practice, we go back to EBSD mode, and if we wish to compare, say, the EDS with the underlying phase, you go to EBSD and click on phase map, and just see that there's very strong similarity between the EDS chemical information and the EBSD structural information. And the final thing, which is very nice, is going to overlay, and we'll make this big for clarity, is you right click on there, and now you'll see that any combination of these maps is now possible. So we could do, you can choose whichever you wish. You can have the electron image, you could have the strain map underneath. So you want to try combining the EDS. I can choose the transparency of each, and these can be readily output, so you can judge one variable against another. So that's a very quick run through of just some of the features available for one sample using the EDS EBSD combined quasar